Ladies and gentlemen, welcome back to another video, and today we're doing something very special. We're analyzing Alan Becker's animation versus math, and although I am a very stupid person, so I don't recognize everything, I'm going to do my best because I think a lot of the video is also just math jargon, but then again, I could just be very stupid, but I think it's a blend of both. So we're going to be trying to analyze everything that we possibly can, so let's get into it. So he discovers negative numbers, he discovers -1. And then what happens is he somehow changes -1 to e to the power of I pi. E is Euler's number, and this is a very special number because everything in nature happens to follow this number, and it's named after the mathematician Euler, so that's why it's called Euler's number. The reason we use e for this number is because it's an irrational number. It comes out to about 2.718281828. I think that's an 8. I'm reading this off, by the way, because I'm stupid. 4590452. You see the problem? It's just a little bit long. It's just a little bit inconvenient to write out. So that's why we like to indicate it as e. E to the I pi happens to be -1. And that's just a very cool thing that obviously I can't prove because I'm stupid. So if you want to look up a proof for that, just go ahead and look it up. I think BPRP made a video on it before. And here he's just chasing away E. He places an I and then he pops into another dimension. I think what they're trying to say is that E went into the imaginary dimension. The imaginary dimension is just similar to the X dimension, the Y dimension, but then you got the imaginary dimension. That's the best way I can explain it in simple terms. Never divide by 0. Okay, he learned his lesson. So what he did here is that he defined what an imaginary number is. And this is actually what an imaginary number is by definition. I, which represents an imaginary numbers, happens to equal the square root of -1, and that's just by definition because it's very useful when we're dealing with imaginary numbers. So this is what I is for, and I, by the way, is equal to square root of -1. As I just said, I don't know why I repeated that, but that's what I is. This is just basic math. 2i equals I plus I, because I plus I is 2 i's. We have 1 I here and then 1 I here, and that gives us 2 I. Let's try to make this a little bit simpler to understand. We know that 2 equals 1 plus 1. It's not window, grow up. 1 plus 1, we have 1 here and then another 1 here. So in total, we have 2 1s. So we can actually rewrite this. We can rewrite this as 2 times 1. And this makes sense because we have 2 1s. So we're just rewriting it in another form. We're writing 2 times 1 instead of 1 plus 1. It's just a simplified version of writing 1 plus 1. I times I equals -1. This also makes sense because I times I happens to equal I squared. And this is just a property with anything. If you have x times x, this is going to equal x squared. That's just a basic math property. Recall that I equals square root of -1. So I squared is going to give us square root of -1 squared. The squared and the square root are going to cancel out, and that's going to give us -1. Now he gets I e to the power of I pi. So now that we know I squared equals -1, we know I squared also equals I times I. I times I times I equals I cubed, which also equals I squared times I. I squared we know equals -1. And then I, let's just keep as I. And by the way, I'm writing I just next to -1 because you're allowed to do that in math. This basically just means -1 times I. It's the same thing, just without the multiplication symbol. Don't worry about it. So recall earlier in the video that e to the power, that was a very ugly e. E to the power of I pi equals -1. So we're going to replace -1 with that. We're going to replace it with e I to the pi times I. And with multiplication, you're allowed to switch things around, so we're just going to switch these things around. So this is the exact same thing as I times e I pi. We're allowed to switch things around because that's just a property with multiplication. You can figure that out for yourself. 2 times 3 is the exact same thing as 3 times 2. And for those of you who don't know, the dot symbol is the same thing as the multiplication symbol. It's just easier to write and it looks cleaner. So what we have here is I cubed, or I times I times I, which is what he did in the video, equals I times e to the power of I pi. Again, he tries to go into the imaginary dimension. This part is very cool. This part is actually very creative. He tries to go into the imaginary dimension by giving himself an I, but then The second coming gives him another I, and then he hops back into the real dimension. And let's see what happened here. We have I e to the power of I pi times I. When there's only one I, this number is imaginary. This is the same thing as I times -1, because recall e to the power of I pi is -1. But this entire thing is imaginary because we have an I here. But if we have two i's, we can actually rewrite this as I squared e to the power of I pi. I squared, recall that I is -1. So if we square this, the square and the square root cancel out, and this gives us -1. And this is a real number. I is imaginary, but -1 is very real. So what we actually get here is -1 times e to the power of I pi. And this is a real number. This actually turns out to be +1 because, again, e to the power of I pi, that's going to give us -1. So we have -1 times -1. A -1 number times a negative number is positive. So this is going to give us +1. And that's a real number. And that's why he hopped back into the real dimension. Stay here. So let's take a look at this. -e to the power of I pi equals +1. And this makes sense because we have a negative sign here. So this is a negative of -1 because e to the power of I pi equals -1. The negatives cancel out. They become positive. So what we get is +1. Now let's take a look at the identity in the video. We have negative cosine pi plus I sine pi. Now you need to know your unit circle for this. So if you don't know any trigonometry, you're going to get lost here, but I can't really help you. Cosine of pi, that's going to equal -1. So what we have here is -1. The negatives cancel out. This becomes positive. So this actually becomes +1. And then we have plus I sine pi. We don't really care about the I anymore because sine pi happens to equal 0. And anything times 0 is 0. So this is going to be 0. And this ends up being +1. And this checks out because these two are equal. So this is equal to this. Here he's just drawing a parabola. That's just, just math jargon. Just having a little bit of fun. I guess you can do that in the math universe. Where even is he? Is he in a calculator? Okay, here we go. This is the imaginary axis. He discovered the imaginary axis. That's the real axis. This, I am actually quite confused on. I don't know what he's trying to say here because, again, I could just be very stupid, but from what I know, this is completely meaningless. I think what he was initially trying to do was draw the unit circle. The unit circle is something in trigonometry that we use a lot, again, just for angles, radians. The unit circle is something like this. We have 1, 0 here, 0, 1, -1, 0, and then 0, -1. And this is just on a coordinate plane. So imagine this circle is on a coordinate plane where, that would make more sense. I probably should have drawn the coordinate plane earlier, but the circle's on a coordinate plane. So I think that's what they're trying to say, because a circle with I, -I, 1, and -1 is sort of meaningless. So I'm not sure what they're trying to say here, or maybe it's something just I don't understand because I'm stupid. Okay, here he discovers radians. Radians are just another form of measurement. It's just another way of writing angles. For example, 30 degrees equals pi over 6. We use radians because they can interact with normal numbers. You can't really multiply a real number by 30 degrees. If you're doing some equation thing, using 30 degrees doesn't really work just because of the degree symbol, so we use it in radians. By definition, a radian is the arc length divided by the radius. If you want to convert a radian to a degree number, you can multiply it by 180 degrees over pi. And let's see if this checks out. 180 divided by 6, that's going to give us 30. So we end up with 30 degrees, and this checks out. And if you want to convert degrees to radians, you can just do the opposite. Let's try that. Let's convert 30 degrees. We just we put pi on the numerator, 180 in the denominator. this checks out to be pi over 6, and just pretend the degree symbols cancel out. That's what we like to do in math. So this also checks out. Again, we're just converting them back and forth. Radians are just another way of writing angles, except we use them a lot because they don't have the degree symbol. So I'm pretty certain they were trying to do the unit circles. So again, the imaginary numbers, -1, +1, don't really mean anything. He discovers what a radius is. Now, I'm not sure what they were trying to do here. Again, let's go back to the definition of a radian. A radian is the arc length divided by the radius. Let's write the radian as theta. This is just the symbol theta. We like to use it for angles, so we're going to use it here. And that's what they use in the video too. The radius we're just going to define as r. Arc length, let's just write it as a for now. So this is radius, this is arc length, and this is the angle. What he did here was the arc length divided by r, and that gave him pi when he was at 180 degrees, which doesn't really make sense. I think what they were trying to write was arc length. I think this theta over here is supposed to be the arc length. I think. But I got about 2 hours of sleep last night, and I just saw this video in the morning. So if I make a mistake, that's my excuse. But I'm pretty sure I'm not tripping here. I think they're just... I think this is just a mistake on their part. He discovers the sine curve. Let's see if this is right. Okay, it is right so far. The sine curve is correct. Cosine curve is also correct. I sine. Whoa, no. That's, nope, no, that's illegal. That's, you can't, nope. So I think this is why they wrote I here, just for the plot. They made this the imaginary dimensions just for the plot. I think this is just for the plot, is what I'm seeing. This is just a sum. It's actually it's in the wrong direction. It's for the intense battle. So for those of you who don't know, this is called sigma. The symbol here is called sigma, and we use it to add numbers up. Normally we use letters like N or K. We use K a lot, so let's use K in this example. But since they're using N, let's use N. And we use it to add things up. So let's say if we had this set to 4 and we had this set to 1, and we wanted this for 5. I'm not going to explain this in too much detail because that's just going to take way too long. If we want to sum up 5, we're going to start at 1. So we have 5 plus, and then we have another one, 5 plus 5 plus 5. Notice how there's 4 of these. We start at 1, then we go to 2, 3, and 4. And I know this explanation is not going to make sense, but I don't really care enough to make it make sense because we're on limited time here. But if we have something like, if we want to start at 2, when we have 5, then we're going to start at 2. So this is the second one, this is the third one, and this is the fourth one, and this is going to give us 15. So notice how that's the difference. The starting point matters. It determines the number of stuff. Now, what if we make it a little bit more complex? Let's make it start at 1, let's make it end at 5, let's make it 2n. What does this mean? It's 2 times the variable n. We're going to start at 1, 2 times 1, plus, and then we're going to move up to 2, 2 times 2, plus 2 times 3, plus 2 times 4, plus 2 times 5. So this is going to end up being 2. This becomes 2. This becomes 4. This becomes 6. This becomes 8. This is 10. All this together. This becomes 10. This becomes 10. This is going to give us 30. Now, what if we change the starting point? Let's start at 2 now. So what we're going to do is we're going to start at 2 first instead of starting at 1. So we're going to have to write 2 first, and then we're going to go up to 5. Plus 2, and we're at 3 now, plus 2, and we're at 4, plus 2, and we're at 5. And for those of you who don't know what the parentheses means, it's the same thing as multiplication, but if you don't know that, then you probably really should not be watching this video. And this sums out to this. This is going to give us 10. Now what we get is 28. So it's just 2 off, but that's the difference between the starting points. So this is what summation does. It adds numbers up in a consecutive order. It goes from 2 to 3 to 4 to 5. Obviously, when we did the initial example where we only used 5, there is no n. So that's why we could just add it from we could just add itself, because, you know, it doesn't matter. There's no n to change the number. But here we actually do have an n to change the number, and that's why it keeps changing. It keeps going from 2 to 3 to 4. So that's what we did. This makes sense because you have r here. I assume that represents the radius. And then you have theta times e to the power of I pi. And recall that this number here is -1. A negative number times a negative number is positive, so this is going to come out to er plus pi. And, you know, both of these sides equal each other, so that's right. Okay, tangent. Whoa, 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 what the? Wait. Okay, tangent times 9, that's 9 times tangent dot. You can't do that. This is a function. So basically what this is saying is this is a function of dot. So functions output numbers. So here, that right there, that graph, that's a tangent graph. That is tangent x. If you want to graph that on Desmos, if you want to try your graphing calculator, that is the graph you're going to get. What he did was he combined tangent with 9. That's not really relevant at all. And he's basically launching tangent graphs and the dot at e to the power of I pi. Pi r squared, that's the area of the circle. I hope everyone knows that a equals pi r squared. I'm going to be very disappointed. Now this part I saw earlier, this part makes me cry. You can't do that. You can't do that. If you do this, your math teacher will kill you, unless they're a bad math teacher. Infinity is not a number. I gotta make this very clear. Infinity is not a number. Infinity goes on forever, but it's not a number. You can't do this. But I get what they're trying to say with it. I get the whole, you know, idea behind the same thing. This I'm too lazy to prove. I don't think I even can prove it. Okay, I don't think. I'm pretty sure a lot of this is just jargon. I don't know if they actually went through the effort of making all of this actually true. If they did, you know, bravo on them. But there might be a few mistakes. I'm not gonna check over this. Yeah, that's too much work. Okay, that's an integral. 0 to infinity. Oh my god. You can't do that. You can't do that. There's no point. That it's a definite integral. If you're going indefinite, then you don't need this number here or this number here. What you're supposed to, this thing here gives you the area under a curve. That's the simplest way I can explain what an integral is, because if I actually do, it's gonna take way too long. But that's the basic idea of what a definite integral does. It finds the area under a curve. So let's say you had the function. You had some function. Let's just say the function was this. A function is just something graphed out. That's the simplest way I can put it. Again, I'm putting things in very simple terms. So if you're a math wizard here, you can correct me, but just know that I'm putting things in very simple terms. If you're trying to find the area of the curve, let's say from -1 to 3, you want to find this stuff here, the area. You can write an integral. You can do -1 to 3 of f of x. But just make sure to write dx at the end. You always got to write d of x, or, you know, the other, whatchamacallit, differential. You got to write the differential at the end, and this is going to give you the area under a curve. And that's even more cursed, actually, because, well, 1, they wrote infinity here, which it's not a number. You can't do that. And 2, they didn't even write, as far as I know, they did not write the differential, so that is just absolutely cursed. So, again, this is just completely meaningless. Okay. The dimension's breaking apart. I'm not sure why that's the case. I got the laser was a little bit too hot or something. Okay, he hops back into the real number system, the real plane. And by the way, the real plane is just x and y. It's just real numbers, the numbers you see every day. Imaginary numbers, I'd say most people do not encounter on a daily basis. I to the power of 4 does equal 1. And let's prove this actually very quickly. I times I times I times I. We're just going to group this. This over here becomes I squared. And this over here becomes I squared as well. Recall I is square root of -1. So I squared is square root of -1 squared. The square root and the square root cancel out. So we get -1 times -1. And this becomes +1, which is exactly what happens in the video. So I think what he's trying to say is that you can't get to the imaginary dimension like that. Or he's trying to get to some dimension. I don't know what dimension he's trying to get to. This is the part of the plot where I got lost earlier. I'm still lost. I thought I was just really sleepy. I could still be very sleepy, but again, I don't know. He's raising the laser. Okay, it's just I don't know that symbol. I've never seen that symbol in my life. 2n, this is kind of useless. I don't even know if you're allowed to do that. I'm not sure. I'm pretty sure you're not allowed to do this, and if you are, then it's kind of useless because you're doing an infinite sum. You just want n is your starting point. 2n equals 0, so your starting point would be the same as n equals 0. So this I think is just math jargon. I'm not even sure what the symbol does. This you cannot do. Holy crap. Allegedly that becomes -1, but obviously I guess maybe it's. Are they just taking the normal sum? Because obviously this as infinity doesn't make sense. Again, infinity is not a number. You cannot do that. That's just absolutely illegal. I guess maybe that equals -1. I don't know. I don't know how much they fact checked it. And this is the end. And yeah, that's pretty much it. Again, I am very stupid, so I might have gotten quite a few things wrong. But if you want to correct me, leave a comment. If you don't, then don't leave a comment, I guess. Jeez, okay, get out of here. Goodbye.